Okay, so in this video what we'll be looking at is a couple of different ways to express some sort of cyclical phenomenon using graphics and math. All right, so let's take for example cyclical math phenomenon first of all. So let's say we have some sort of a spring here with a mass that's connected to it. All right, and I was to, let's say, pull on this spring, and actually before I pull on the spring, let's indicate here first of all that if no outside forces are acting on this spring with the exception of gravity, then this spring is going to be at some sort of a, what we call it, equilibrium. Okay, now if I was to pull on this spring or the masses at the bottom here, let's say I pulled downward, okay, which means I'm now adding an outside force to this system here. What will happen is when I release the spring and the mass and the spring will go up, then it will come down, then it will go up, and then it will come down, so on and so forth in a cyclical pattern. Okay, meaning it's just repeating itself over and over in some sort of a timely manner, you can say. All right, so as I was saying, we can actually model this sort of a behavior here, let's say in two different ways. Let's start off first with the graphical. Okay, so to represent this in a graphical manner, all right, we can have we can have a, let's say, an XY graph here, XY, where on our y-axis what we're going to be representing is the amplitude of this phenomenon, meaning how high the object goes, how low it goes down from equilibrium. Okay, so equilibrium would be our axis here, which is the x-axis, or the zero axis on the y, if you will. Okay, and as the object goes up, it will go above equilibrium. As it comes down, it will be below equilibrium. All right, and on our x-axis, what we'll do is we'll put time on our x-axis. All right, so on our x-axis we have time again, okay, and on our y-axis we have amplitude. So for the object that's moving up and down here, it will again be moving up and down in some sort of a cyclical fashion as time moves on. All right. Okay, to represent this same phenomenon, let's say mathematically, all right, we may use sine and cosine, and you may be familiar with. So let's say we say that the function y, or pardon me, y as a function of time, all right, we can say that that is equal to some amplitude sine of omega t, where omega, all right, is equal to 2 pi f, and by the way, f is equal to the frequency at which the cyclical phenomenon is moving up and down. Okay, and omega, we call this the angular frequency. All right, so for an object, let's say that if we were to represent a cyclical phenomenon using this equation up here, what we would end up with is an XY graph here, where on our x-axis we have time and our y-axis we have amplitude. It will turn out looking like this, okay, or something similar to this, where the A, and let me write amplitude here, or I'll just leave it as amp. A here is the maximum amplitude that it reaches, and then down here we have negative A, which means it's the minimum amplitude that it reaches, and in the middle right here, this is our equilibrium. And as time goes along, it just goes up and down, and so forth. One thing I did not mention here above, when we were talking about the frequency is equal to 1 over the period. Okay, frequency is equal to 1 over the period, and a period is, let's say we pick this point right here. Note that the sine wave is going up at this point right here. So what we do is we look for the next time that the sine wave is heading up, and that time in between there from here to here would be equal to 1 period. Let me write a t here again. Okay, so this will be equal to 1 period. So you just pick one point on the graph and then find an equivalent point later on that'll be equal to 1 period. So if I pick this point here and I pick this point here, the distance, or not the distance, but the time that's found in between here and here, that's also equal to a period. Okay, so this is how we would represent this sine wave using this phenomenon here, using this equation for a sine wave and this graph here for the sine wave. Now, one thing to notice is that at time t equals 0, okay, what we're saying is that the distance from the equilibrium is going to be equal in this, or 0 in this case. So if we have that spring that we were talking about, okay, and let's say we had a timer in our hands, the time at which we start the timer, which is timer t equals 0, the spring and the masses here, this entire system will be at equilibrium. Okay, so that's what this is saying here. So we start timing, it's at equilibrium in terms of its motion, and it probably goes well, based off of our sine wave over here, it's going up and then it's coming down, up, coming down, so on and so forth. Okay, so again, at the time you start timing, that's where it is in terms of its progression. It's at 0 and it's going up and it's coming down, it's going up and coming down. And so this phenomenon here is described by this graph, which is also described by this equation over here. All right, so let's say, for instance, now I mentioned before, we can also express the phenomenon using cosine. Okay, we can also represent it using cosine. So if you recall, for a cosine wave starts at its maximum amplitude, goes down, up, so on and so forth. Okay, and again, on our x-axis we have time, and our y-axis we have amplitude. Okay, and so the equation for this then would be y of t is equal to amplitude cosine omega t, okay, which is very similar to what we had before, except that now we're using cosine. Okay, so this is y as a function of time is equal to a cosine omega t. All right, so same thing before, omega is equal to 2 pi f. F is equal to frequency, and 1 over period is equal to the frequency. All right, so in terms of our phenomenon in this case, which was that box or masses on a spring here, what this would mean then is that equilibrium is somewhere, let's say, down here. Okay, at time t equals 0, and we start time t equals 0, that means the box is at its highest point here. Equilibrium is somewhere down here, and so when we start timing, the box is actually going to start by going down first past our equilibrium point, then coming back up past the equilibrium point, down, and so forth. All right, so this phenomenon here, the cyclical phenomenon, is described by this graph up here, this cosine graph, and this equation. All right, so now one of the things that you may or may not have noted is that the two graphs here, both my sine and my cosine, are actually pretty similar. The difference between the two, and what I'll do is go ahead and write the two of them on one page. So let's say this is our sine here, and this is our cosine. Okay, and it's not, in terms of our frequency, it isn't perfect, but you get the idea in terms of here being my maximum amplitude, and so therefore this is cosine, this being equilibrium, so this is a sine. Okay, now what you'll notice is that with the two of these, the two of the graphs here look pretty similar, with the exception of there seems to be some sort of a shift between the two graphs. Okay, there seems to be some sort of shift. The sine waves are pretty similar. It's just that one begins when the amplitude is at 1, the other one begins when the amplitude is at 0. So what we can do is, let's say we wanted to represent the cosine wave here. So we're talking about this cosine wave, and we wanted to represent it using a sine. We have to find a way mathematically, let's say, if we wanted to do that, to represent this cosine wave, let's say using a sine equation. So what we're saying is we have the function y of t, which is equal to a sine omega t, and what we're going to do is introduce what's called a phase shift. A phase shift. We're using the Greek letter delta for that. Okay, and what this will allow us to do then is this will allow us to represent our cosine wave here, but using the sine function. Okay, so what we note is that when we have y at time t equals 0, we have that we have our function here at its highest amplitude, sine omega, let's go ahead and put 0 in there, plus this phase angle, or this phase shift, all right? And when it's at its highest amplitude there, that means this y of 0 here is equal to a, which means this is a is equal to a sine omega times 0 here will give me 0, so then we're just left with the phase shift in this case. Okay, and so therefore I can divide both sides by a, which gives me 1 over here is equal to sine of that phase shift. So we can find what this phase shift is equal to by taking the inverse sine here of 1, which is equal to the phase shift, and that will tell us what the phase shift is between, if we were to use the mathematical function sine to represent this cosine wave that's up here. And if you go ahead and calculate that out, what you'll notice is that you end up with a phase shift of 90 degrees for that phase shift. Okay, so if we were asked to find the mathematical function or expression that represents this cosine wave up here, or what looks like a cosine wave, we'll just say, using a sine function, we can go about solving in this manner here in order to figure out what the phase shift is equal to, okay, in order to do so. All right, so again, what this video was on was just how you go about expressing some phenomena. In this case, what I used was the phenomena in this case was a spring that was going up and down after some force had been applied to it, and then I took that phenomena and expressed the phenomena both in a graphical way, okay, using graphs, and also I expressed it in a mathematical way, and then I showed you how to go between the two. Let's say if you needed to represent the phenomenon, which happens to be this way, but you're asked to do it using a sine wave, how would you go about actually solving that? And so you can do the exact same thing as long as you know what the amplitude is at 0. Okay, let's say if for instance you had a sine wave and you're asked to represent that sine wave, you're asked to represent that sine wave using cosine, you do the exact same thing. Y of t is equal to, in this case, a cosine, okay, of omega t plus that phase shift. All right, and you know that y of t in this case would be equal to 0, and t, because you're looking at time t equals 0, that will be equal to 0 also, and which just leaves you with this, and you can actually go through and solve for the phase shift, and that way you'll be able to express this as a cosine. All right, so thank you very much, and please do check out my website for additional tutorials, and my YouTube channel for additional tutorials.